Hello, am I audible? Hello. Hello, am I audible? Can respond once in the chat. Okay, let's get started. Hope I am audible. I can't. Hello, am I audible? Can someone confirm in the chat, please? Okay, right. Let's get started. I'm hoping I'm audible. So I'll start. So I welcome you all to the Week 7 Operating System Fundamentals interactive session. So in the last week, Week 7, basically the topics covered is on process synchronization, critical section problem, the properties that the solution of a critical section problem should cover, and various solutions for this problem. So let's get started one by one. So before getting started, what was a critical section? So let me share another screen. Basically, a critical. Yeah, sure. Yeah, probably my audio is too low. Right. Is it better? Better now? Okay, thank you. Yeah, basically, when we say critical section problems, what we mean by is when we have some n different processes trying to access a common shared section of code. There is a synchronization has to happen between these processes so that we will always have a consistent view of the data accessed across these processes, right? So, a solution to any critical section has to meet three properties. One is mutual exclusion, another is progress, and the third one is bounded waiting. So, if there are process P1, P2, Pn trying to access a common area called critical section, then any solution to this critical section problem should have meet these three properties. So by mutual exclusion, we mean that at any given point of time, only one process should be accessing the critical section. Progress means that if no one is executing in the critical section and some other and another process want to enter into the critical section, then its access to the critical section should not be postponed indefinitely. So if any process request for a critical section access, it has to be allowed to enter within a definite period of time. And bounded waiting means that if some process is already running in the critical section and another process is requesting to enter, then there is a limit to the number of times this process can enter before the request is granted. So the already executing process, it just cannot keep on entering into the critical session without serving the other requests. That is bounded waiting. Okay. So any process, any solution that we propose should meet these three criterias. So first, let's get started with. We'll see couple of solutions that help us ensure this properties and ensure that processes are synchronized. Okay, so one software solution is Peterson's algorithm. Okay, so we can see that first. So this is an software solution, and this solution considers only two processes. Okay, so in the solution, it consider majorly two variables. One is a turn variable, and the other is a flag. That's kind of an array. Okay. So there are these two variables, and using these, it ensures that when two processes are trying to enter the critical section, they are synchronized and they enter one after another. Okay, so the algorithm is like this: flag of I equal to true if it is in process I, then turn is equal to j. So flag of I tells, so this flag array, it tells whether the process wants to enter or it is ready to enter to the critical section. So flag tells whether it is ready to enter, and turn tells which process is it. Again, it tells the turn of the process. Like if turn is set to one, it implies that it's process one's turn. If turn is set to two, it implies that it is process two's turn to enter the critical section. So the same portion of code we will have on both the process, and then we'll see how the synchronization is achieved. So then before entering the critical section, so this is the check done. Flag of J and turn equal to J. If these is met, then it will not enter. Otherwise, it will enter the critical. So this is the algorithm. I'll just quickly note it down. And then the algorithm says equal to, then this is the remainder section. Okay. So this is the y. So what happens is when first if process P1 wants to enter, if P1 wants to enter or P1 is ready to enter, it will set its this flag variable to true. Then it will set the turn for the other process. Okay. Hello. It will set the turn for the other process, and then it will check if flag of J and flag of J is equal to true and turn is equal to J. If the statement is true, it implies that the other process wants to enter and it is its turn. Okay, so the process PI will wait. It will not enter the critical section. It will wait. If any of this condition is not true. For example, this turn of equal to J is set by Pi. Okay, now if the process J was not ready, then flag of J will be false. So then this condition will not be met. So in that scenario, it will directly go and enter the critical section. Okay. Now, after it enter the critical section, it will set, it have already entered the critical section, right? So it will now enter the, set the flag of I, its own flag as false. So that now if the other process wants to enter, it will be able to enter also. Okay. So this is the main check that is done, and so this algorithm actually ensures a mutual exclusion. So how mutual exclusion is ensured that um, at any given point of time, both flag of I can be true and flag of J can also be true, but turn can be only I or J. Turn cannot be I as well as turn can be either I or J. It cannot be both I and J. So based on the value of turn, this so assume that both the process wants to enter. So this two will be true. Now based on the value of I, only one of the process will be able to enter the critical section. Okay. Now, if that process enters the critical section, once it comes out, it makes its turn as false, right? It makes its readiness to be false. So next time when the next process tries, it will be able to enter the critical session. So with the help of flag and turn variables, we are ensuring that it at most once it has to wait and it gets access to the critical section, and also, if it have requested to enter the critical section, then and if the other process have not showed interest, then it will be able to enter its critical section. So both progress and mutual exclusion and bounded waiting is actually met by this algorithm. Okay, so in this majority of the critical section algorithms that this is a software algorithm and this is not actually in use. Okay, because majority of these instructions are not atomic, so that itself will have issues. But we will be looking at other algorithms that are normally used in real scenarios. But most of these, as we can see, we are doing looping on a while, right? This is called as busy loop or busy waiting. Okay, and these solutions are normally considered wasting the CPU a lot, because even when it is waiting on this while loop, the CPU is actually being utilized, but without doing any work, right? So this busy waiting solutions are not considered as efficient solutions. So another solution, the other solution that we will look at are a couple of hardware related solution, and then mutex and semaphores. Okay, so in general, critical section problems are solved by using a general terminology we can use is like we use locks. In general, critical section problems are solved using what is known as logs. So when we need synchronization when there is either sharing of resources or sharing of code, sharing of variables. When there is a sharing, we need to do the sharing in a synchronized manner, and that is why we need this synchronization, right? Synchronization solutions, because these shared resources or variables are accessed in the proper manner. Okay, so one way to ensure that they are accessed in the proper manner is by using locks. So whoever wants to use it will take the lock and then use it and then release the lock, or we call it as there is before using it you acquire the lock, then you execute the critical section, then you release the lock. So this is in general, this is will be the template of the solution. How this acquire lock and how the release lock is designed varies based on the solution, but this will be the a general template of a critical section problem will look typically like this. Though it will be there will be what is known as acquire lock. This will be in the entry code. Entry. Critical section entry code. Then you will enter the critical section. Once that is done, there will be a release code. Release log. This is the exit code. And then we will have the remainder section. So this will be the typical template for a critical section problem in general. But how this is done is what is going to vary. Okay. So now we will see some hardware solutions, like if we have some certain hardware operations or hardware instructions which do a set of operations in an uninterrupted or in an atomic fashion, then we can achieve this acquire lock and release lock using those instructions. Okay. So one such type of hardware mechanism provided is uh, hardware synchronization. Okay. One is test and set, and the other is swap. Okay. There are two such hardware solutions provided. One is test and set, the other is swap. Okay. So in the test and set instruction, how what happens is this particular instruction will set the value of that the variable or the target to true. It will and return the current value. So how it is, so boolean test and set. So it will return the current value. It will set the target value to true and return the. So this is the test and set operation. Okay, so this can be this is the particular implementation. So this can be used to come up with a solution for critical section. So how we do this is we will use a Boolean variable called lock, and we can use instead of acquire lock. What we will do is we need while test and set of lock, do nothing. Otherwise, you enter the critical section. Then you say after that you set lock equal to false. So initially the value of lock is initialized to true. So how it works is, so initially lock is having false, okay. So this test and set will return the initial value. So it will return false. So while of false, so it will go to the critical section. So now in between, if another process is also trying to do a enter the critical section. So what happens is test and set. So suppose we have two process P1 and P2, and P1 executes this, tries to execute, enter the critical section. So when P1 execute test and set, the log value is false. Hmm? But inside this function, the lock will be finally set to true. Lock will be set to true. But when P1 sees this, since the initial value was false, it will come false here. So P1 will enter the critical section. But when P2 executes it, since the lock value is set to true, this will return the value as true for P2. So it will be going in the loop until P1 completes the critical section and set it to false again. So this is how we can use the test and set for hardware like synchronization. Okay, but here again the solution is having busy waiting, and this doesn't ensure bounded waiting and all. Okay, so there is a mechanism uh, to bring in bounded waiting using additional variable like waiting and other array of variables we can use, and there's a variation of this available which ensures that bounded waiting can be met. Okay, so that is there. The another instruction is another hardware mechanism is the compare and swap instruction. So in compare and swap, what it does is here it will there will be again one lock value. So it will compare it with the expected value and then assign it to the new value. So the instruction here is compare and swap. Can you please mute yourself? So here inside this what it does is it will first copy the value to temp. Then it checks if the value equal to expected. Then if it is so, then it will set it to the new value. And then it will return the old value. So this is what compare and swap does. This also we can use it for locking. So how we will use this is mm, here again we will have a lock variable. We will have a variable lock which is initialized to 0. So how the function looks is, so while compare and swap, we have log, the expected value is 0 and the new value is 1. So if the value of log is 0, you set it to 1 and return the old value. And if this old value is, if the old value is 0, then we are going to enter the critical section. Okay. Do nothing, otherwise critical section. Then after that, you again set lock equal to 0. And then the remainder section, and then so now here what happens is if two process P1 and P2 is executing this, so when initially we have kept the value of lock to 0. So if P1 executes lock P1 executes this lock 0, 1, this is the expected value is 0 and the value of lock is also 0. So this if check will be met. Okay, this if check will be met. And then the new value of lock will be set to 1 and the old value 0 will be returned. So while not equal to 0, it is going to busy wait, but current we got the value as 0, which implies that this is entering the critical section. Now, when P2 comes, P2 will again call like this only log 0, 1, but at that time the value of log is already 1. We had made it to 1. So 0 value expected and this will not match. So it will not change the value. So value will still be 1 and it will return the value as 1. Okay. So this will be met and P2 will go into this wait. Once P1 completes the execution, it will change the value of lock equal to 0. At that time, when P2 invokes this, again, the value of lock is 0, expected is 0. And then it will get the value returned as 0, and then P2 will enter the critical section. Okay. So this is how these two hardware instructions can be used for ensuring synchronization. Okay, so these two are actually hardware methods, and these are not normally used by application programmers. Okay, they are normally provided at the hardware end. So in general, the the APIs or the solution for synchronization solution that are provided and commonly used ones are one is mutex and the other is semaphores. These are the most commonly used solutions. Okay, in the code. So mutex lock is nothing but it's one of the simplest tool. It's a short form of mutual exclusion. Mutex lock. Okay, so here we have two operations for mutex lock. Available and release. Okay, so sorry, acquire and release, these are the two operations with mutex. With mutex, the two operations available are one is acquire, the other is release, as we saw earlier, and there is this boolean variable called available. Boolean variable called available. Based on its value, we will either enter the critical section or we will wait. Okay. So the two operations are acquire Acquire is defined as while not of available. If available is 0, then not of available will be 1. Then we go for a busy wait. Otherwise, we enter the critical section, we make it false and enter the this acquire function ends here, and after acquire function will return. So after acquire, we will enter the critical section. So release is release is nothing but available equal to true. So these are the two functions. So in general, what will happen is if somebody have a critical section problem, so we will call acquire, then critical section, and then we will call release. So this is how it will be. So when acquire is called, we will check if available is 0 or 1, true or false. If available is true, available is true, then not of true is false, right? So while of false will exit, then we will make available false because already this process is entering the critical section. So we'll make available false. Then once a critical section is entered, we will it is executed. We will call release. In the release again, available will be made true. Okay, so when this at this point, if another process also calls the same set of routine, this acquire will not acquire function will go into this busy wait. So acquire function will not return, and that process will not go to the critical section because available value is made false by this particular the first process. So while of false will be while not of false, right? It will be while true. So it will get into this busy wait. So this is how simple mutex locks work. Or we can use it using like a lock also. Okay, I mean terminology carries it. So acquire lock, critical section, release lock, and remainder section. That is how the usage will be. So acquire lock or critical section, then release lock, then remainder section. This is how this works. The other primitive is semaphores. It's also similar only, but instead we have an integer s, which is an integer. So mutex is mainly used for two processes. Okay. Or it's a like no, not two processor. It's a we call it binary kind of because it's either you enter or not enter. You cannot allow multiple people to enter or something on that line. Okay, so whereas in semaphores, it's a s is an integer variable. So here, in place of acquire and release, the two operations, the atomic operations that are used is wait and signal. So these are the two operations. The definition of wait is wait of S is while S less than or equal to 0, we do a busy wait. Otherwise, we decrease the value of S. Okay, so that is the wait operation. Signal operation is signal of S will simply increment the value of S. Okay, now let's assume we have two processes P1 and P2. who is trying to who have this critical section process, like critical section, how it is written as we have weight of S, then we will have the critical section, then we will have the signal of S. Now, when P1 assume that S is equal to 1 initially. When P1 execute weight of S, so what happens is when S is less than or equal to 0, it is not less than or equal to 0. So it will become S equal to S minus 1. So S will become 0 and this weight will return. It doesn't get into a busy weight, it will return. So it will P1 will enter the critical section. Now, when P1 is executing in the critical section, if the value of S is now 0, P2 will also execute the same weight of S. So when it goes here, weight of S, again now the value of S is 0. So S is less than or equal to 0 is a true statement. So again, so P2 will get into a busy wait here. Okay, it will be looping here. Now, once P1 completes the critical section, it will do a signal operation. Signal again makes the value, increment the value of S. So S will again become 1 after S equal to S minus 1. So at that point, P2 is looping here busily. So at that point, the moment S becomes 1, this check S less than or equal to 0 will fail. And then again, P2 will make the value of S 0 and will enter its critical section. This is how semaphores are used for ensuring that only any given point of time, one of the process is executing in the critical section. Then there are different types of semaphores, such as counting semaphores and binary semaphores. Binary semaphores are nothing but similar to our mutex log. So it will have only value 0 and 1, whereas counting semaphores can have the value of S can be, if I initialize the value of S is equal to 3 in place of 1. What happens here? And if I maintain the same weight and signal, then it implies that three processes can enter the critical section at any given point of time. There will be, in some scenarios, we may have to share some resources between the processes. In such cases and all, we can allow actually more than one process to share the resource and all that. So in such scenarios, we normally use the counting semaphores in the for if so based on the value that we initialize, that many number of process can be in the critical section or can be sharing that critical section. So that is counting semaphore. So here, if we make the value of S equal to 3, and if we have P1, P2, P3 and P4. If they arrive in this order, so initially P1 will wait. All of them will have a weight of S, critical section and signal of S. P1 will have it. P2 will have weight of S, critical section and signal of S. P3 will also have weight of S, critical section, signal of S. And P4 also will have this. And now if they all come in this order, so this weight of S initially S equal to 3. So this weight of S will see that the value of S is 3. So it will decrease it to 2. And when P2 gets in, P2 see that the value of S is 2. It will inside its weight call, it will make it to 1. Now P3 and it will enter the critical section. P3 will see in the weight that S equal to 1. it will make it to 0 and it will come out of the wait call and enter the critical section. Whereas when P4 does this wait on S, it will get into a busy wait because the value of S is 0. So this gets into busy wait. It will not enter the critical section. Now once P1 completes, once the P1 completes, it will do a signal of S. Then the value of S will become 1 and then it will enter the critical section. Now when this do a signal, it will become again 1 because this would have made it 0. When it signals, this will become 2 and when it signals, it will become 3. So if we have the counting, the counting semaphore value set to n, then it implies n of them can be in the critical section at a given point of time. Yeah. So so one of the major difficulty with is that the busy waiting, right? So busy waiting, as we have seen, is a literal waste of CPU. So in place of busy waiting, there is another option to block the particular process, which is waiting for a semaphore. And when another process signals it, we can wake up the process. So that is another approach. So in such scenario, what we will have is every semaphore will have a waiting queue. So if we need to avoid the no, if we don't want busy waiting, then every semaphore will have a queue associated with it. So that queue will have the list of all processes waiting to get that particular lock. Processes waiting for that lock. Okay, so we will have it, a list will be maintained for a particular a semaphore, and when a process gets into this busy waiting mode, it block itself. Instead of going to busy waiting, it will block itself and add it to this queue. Then when another process release the lock, there will be a wake up done. And with the wake up, then this process will get access and it will start execution. Also, this is another way of avoiding busy waiting. So how it looks like this. So in our weight of S, in place of an integer, we will have now S will be a structure with some link and all that. So we will use a semaphore. Yes, okay. So in this, as usual, we will make the value minus minus, and if S value is less than 0, then add this process to S dot list. And then we do a block here. Okay, so this is the wait. Same way, signal will have we increment the value, and if 0, it implies that we have some processes in the list. So we'll remove the process from the list. And then we wake up that process. So this is with this one can avoid. So in the wait, what we have this added thing is we are adding it to the list and then we are blocking that process. Whereas in the signal, we are removing it from the list, and then we are waking it up. So this is the difference. So this here there is no busy waiting or no infinite while loop or while loop busy waiting going on. Okay, so this is one way to avoid busy waiting. So, though we have these mechanisms to ensure that processes access the critical section in an ordered manner, these approaches do have certain limitations. Sometimes this semaphores can actually lead to what is known as deadlock and starvation. So, deadlock is a scenario. So, deadlock, what is deadlock? Deadlock is a scenario wherein multiple processes are waiting indefinitely for an event to occur, and each of this event has to happen due to the other waiting process. So, I think probably with an example, it will become clear. So, assume we have P naught and P1, and these are the set of, and we have two semaphores, S and Q. So, in P1, we have what is known as P, and then followed by weight of Q. Whereas in P1, we are doing a weight on Q and then followed by a weight on S. Okay. Then after some time, we do a signal of S, and then in P1 we do a signal of Q. Same way we do a signal of Q and then signal of S. So here what the problem is, here P naught is first waiting on S. Okay, it invokes S, so the value of S becomes X get decremented by 1, and then it is doing a wait on Q. Whereas here P1 is already have invoked weight of Q and thus decremented its value, and its value is now 0. After that, it is calling wait on S. So, but already P naught have taken this lock. So P naught have taken S semaphore S lock, and P1 have taken Q lock. After that, P naught is trying to take the Q lock, which P1 already have. So P naught will not be able to move further. So it gets stuck here, stuck at this point. Same way, P1 have already taken the Q lock, and it's trying to acquire the S lock. But S log is already with P naught. So P1 will also get stuck at this point and it will not be able to proceed. So P naught is waiting for a signal of Q from P1, whereas P1 is waiting for a signal of S from P naught. So both of them are waiting for an event from the other proceed, and both are waiting on each other, and this leads to what is known as a deadlock situation. So if when we are using with some of those locks, if we don't handle these situations properly, there is possibility that we get into such scenarios. Another issue with this is the starvation. So there is a possibility that one of the semaphore can just get queued up in that list, and it doesn't get the wake up call at all. If that happens, then it's like indefinite blocking and the process will be able to enter into the critical section. So that scenario is called as starvation. And another scenario is like the what is known as priority inversion. So here what happens is, again, suppose we have process P1 and process P1 is entering. Okay, there is a wait of S and it got into critical section, so it is executing in the critical section. At that time, a high priority process called P2 came. Now P2 also have wait on S and critical section. So now if a high priority job comes, this P2 will be scheduled, but P2 will call wait of S. But since already P1 have taken the lock of S, this he will not be P2 will not be able to proceed. And since P2 is having high priority job, P1 will also won't be given the CPU. So it is equivalent of P2 has to wait for a process whose priority is much lesser than this. It's kind of a situation as if P2 have lower priority than P1. So this scenario is called priority inversion. And in one of the solution is what is known as priority inherent. So in the solution, what they do is if a P1 is the low priority job here, and if P1 is accessing any section which is also will be accessed by a high priority job, then P1's priority will increase to that of P2. Okay, so that when P1 P2 comes, P1 is also at the same priority, right? So P2 will not be preempted, and P1 will not be preempted for P2. So P1 will, so that P1 will continue to execute. It will execute the critical section and then it will do the signal. So to ensure this, there this priority inheritance is used. And so this is another one thing. And there are the other issues with majorly most common issue with the semaphore is that incorrect use of semaphore operation. So as we see, a wait has to be followed by a signal. Right? A wait has to be followed by a signal. What will happen if a wait is followed by a wait? Or a instead of wait and signal, if somebody code signal and signal. So this scenario is like a deadlock. This will be like more than two process in critical section. So these are all critical issues if we don't manage these signal and wait, this pair of combinations properly. Okay, so if this is not, this is the right way, this is the wrong, and this is wrong. So if we don't take care of doing these things in the proper manner, there is always a possibility of deadlock and starvation to occur. Okay. So this one of the solution to these things is like high level programming language constructs such as monitors. Okay, so in monitors, one need not worry about ensuring that for every weight I have added the respective signal and all that. So this they give this monitor construct that will ensure that only one particular process will be executing inside the monitor at any given point of time. So that is the concept of monitor. It takes away these implementation things from the programmer, and so that it makes it much easier for the programmers to achieve synchronization. Now let's see some real time, some examples of what to say, uh, synchronization. Couple of examples discussed about synchronization. So, a couple of classical synchronization problems are one is a bounded buffer problem. Another is readers writers problem, and the third one is dining philosophers problem. So the solutions for these are provided using semaphores, monitors, etc. Okay. So now let's take a bounded buffer problem. So what is a bounded buffer problem? Here, the bounded buffer problem is that, or producer consumer problem is that we have some n number of producers, P1, P2, P3, and Pn, and we have some M consumers, C1, C2, C3, Cm. Okay, and there is this common buffer from which they are reading. So all these people write and this will read. So these people write, consumers will consume. So the rate at which the producers produce and the rate at which the consumers consume may vary. Rate of production and rate of consumption vary. So we need to ensure that producers write if there is an empty slot. Producer write only if there is an empty slot, and consumer consume only if there is a non-empty slot. Right, yeah. So we are using couple of, so this is achieved using a couple of semaphores. So we use three semaphores basically. One is sem mutex, the other is sem full, and the other is sem empty. To ensure that producer writes only if there is an empty slot, and to ensure that consumer consumes only if there is a non-empty slot, we use these three semaphores. Okay, sem mutex is initialized to value 1, sem full is initialized to 0, and sem empty is initialized to 1. Sorry, n. So it is nothing but what is sem full. So when the initially, the buffer is not full, so we are keeping it as 0. So sem full will have the number of like how many content is there. Okay. Sem empty means how many empty slots are currently available. So initially, all the for a buffer of n size, all the n slots are available. Okay. So now let's see how this is achieved. So for a producer using these methods for the producer problem, for the producer code will look like this. So we will have a do, then in the code, we producer should write only if there is empty space, right? So if we wait for empty. If there is an empty space, then we take the mutex for the buffer so that only one of the producer will write. Then we write it, okay? Write the buffer. Then after that, signal mutex, and we have now written one thing to the buffer, right? We have to increment the number. So we signal full. Okay, so full will tell how many how many number of slots are currently full. That will be incremented. Okay, so some empty will decrement this number. So this is the producer consumer code will be consumer code is first we have to we should read only if at least one it is non-empty. So we wait for full. Okay, sem full will tell how many slots have buffer. Okay, so we wait on it. So if it is 0, if this value is 0, we will be waiting here until something is written there, until a signal of full comes. Then we wait for mutex. Then we remove from buffer. Remove from buffer. Then after that, signal mutex, then signal empty. So what happens here is, assume that a producer is trying to write, okay? A producer is trying to write one chunk of buffer. So what it will do is, first it will wait for empty. Okay, it will check whether there is any slot available or not. If there is any empty slot available, then this will return. So this wait of empty will have the buffer full check inside it. Okay, if the buffer is full, then it will go. It will not return. It will go for a busy wait. So this will return. Wait of empty will return only if there is an empty slot. Okay, if there is an empty slot available. Then we take the mutex lock, then this will be returned and we'll release the lock. Then what it will do is we will signal the full. So this will increment the number of buffer, okay, number of available buffer by one. Now, when a consumer comes, it will first check if it is full. If this is full only, it will full in the sense this will return if there is at least one element in the buffer and it is non-zero. Okay, then it will take the lock. It will remove it from the buffer. And once we remove from the buffer, we need to decrease the number of element from the buffer by one. So we are doing a MP. So we are signaling MP because we have removed one element, right? So we signal empty. Okay. So now assume that the buffer is currently full and the producer is trying to write. So when on wait of empty, the producer will go on a loop because it is completely full. On wait of empty. It will be doing a waiting here. Producer will wait here. Now when a consumer comes and read, wait of full will return. It will read, okay, signal of mutex, and then once it reads the content, it will signal an empty. That time one slot became empty, right? So that slot then the producer can use and write. Okay, so this is how the producer consumer problem is handled using semaphores. Another similar classical thing is the readers writers problem. So readers writers problem is so in this readers writer problem. So there is some data set that is shared across many readers and uh, data set that is shared between readers and writers. So the idea here is two multiple readers can read simultaneously. That is possible. Whereas read and write cannot, and multiple write also cannot happen simultaneously. So this is the logic here. So if there are n readers and m writers, R1, R1, R2, Rn, and W1, W2, Wm. all n readers can read simultaneously because nobody is changing the value. So there is no need for a mutual exclusion there. Reading can happen simultaneously. Whereas when someone is writing, when multiple people are writing, it has to be ordered. You know, people cannot write in on the same thing at the same time. It has to be ordered one by one. Same way, when someone is writing, we should not allow anybody to read. Like the writing has to be complete, and only after that the read should happen. Or so that is the logic here. So we need to handle this scenario. That is, multiple readers should be allowed to read, whereas write has should not read and write should not happen together. So here again, we use couple of semaphores, locks to ensure this. So we use two semaphores. One is semaphore read write mutex. This is mutex. This is initialized to 1. And the other is other semaphore is mutex, which is initialized to 1 again. And there is another variable called read count. Is initialized to 0. So read count gives the number of readers simultaneously reading the particular data. So that is what a read count gives. So here in this particular solution, the priority is given to the readers. If somebody is reading, readers are given priority until the reading is done. A write won't be allowed. So how the readers writers problem we can solve with semaphore is, so a writer will be this will be record of the writer. If he wants to write something, first it has to wait for the RW mutex so that nobody else will write. If it gets the lock, then write, and once writing is done, signal release the lock. Okay, so this is right. Here, the reader is slightly complex here. So here, what happens is for reader, what we do is first we get a first we have to increment the number of read count. So for that, this read count is actually a variable that is shared between all the readers. So when all of them, again, that is a right only, so we need to have this the variable secured using a lock. So that is why this mutex is used. Okay. Then now if this read count equal to 1. So that is, this is the first reader. If it is the first reader, then before we start to read, we will check if there is any writer. Okay, if we wait for, if any writer is writing, then we need to wait until the writer finishes. So we do a wait on the read write methods. So if somebody is writing, we will not get this log. If no one is writing, then this log will be available. Okay. Then when this log becomes available, it implies that no one is writing. So that time we signal the mutex so that other readers can read. And now all the readers can read. Readers will read. Okay. Now, once this once this particular reader is done with the reading, again we will take the mutex. We will decrement the read count. Now, if this read count equal to 0, we again signal the text so that if any writer is waiting, he can write. So this is the logic of read. So here what happens is, so suppose we have this order I have a reader. I have a reader. Um, Sorry, let's start with the writer. I have a writer 1 and writer 2, followed by reader 1, followed by writer 3, followed by reader 2, followed by reader 3. Okay. Now let's see how this works. So first writer 1 comes. Hmm. Writer 1 comes, it will check here if weight of RW mutex. Okay, nobody is currently writing. So it will take this lock. Now when W2 comes, W2, writer 2 will again try to take the RW mutex lock. Okay, so it will not be able to get it. So it will go to wait. Now R1 comes. R1 will take the mutex lock. It will increase the read count. And now if you see, it is the first one to read. So it will wait for the RW mutex. RW mutex is not available, right? So it will be waiting here. So R1 will be waiting here. And this W2 also will be waiting here. Now once W1 is written, it will signal and W2 will enter. So here also W2 also will write, it will signal, then it will come here. Then R1 will come. R1 will come out of this busy wait. So now it will then signal and it will be going for reading. Okay. R1 will be going for reading. Now W3 will be trying to write. So W3 when it comes here, weight of RW, it will not get the lock. So W3 will not get the lock, it will wait. Now if R2 comes, R2 will go here. R2 will increment the number count here. It will see read count is 1, no, which means somebody is already reading. Okay, so it will directly go here and it will start reading. R3 will come. R3 will also increment here. Go check here. It is not 1, it is 3 now. So it will go and read. So whoever, if someone is reading, how many ever process comes for read, they all will directly go and read. Okay. Now once R1, if R1 is done, it will decrement the count to 2 and it will see if this is the 0, if it is not 0, right? So it will just only mutex it will release. Now R2 will come, R2 will decrement the count, it will become 1, it is yet not 0. Now R3 will come, R3 will see the count, okay, it is 0. Now it will do a signal of read write mutex. Now once R3 also completes reading, only W3 will further gets to enter its critical section. So this is why we told that the solution gives priority to reader. So if someone is reading, then how many ever other process who wish to read comes, they all will enter and start reading, and the writer process will have to wait until all of them are done with reading. So this was another example of a classical problem of process synchronization. There is one more such problem, which is dining philosopher's problem. This one we will be discussed in the, we can discuss this in the next class. Okay. Now we can go to the question answers from the previous year. So the first question that was discussed in the previous year, the first question is, which of the following is incorrect about monitors? So monitors is a high-level abstraction that provides a convenient and effective mechanism for process synchronization. It's a high-level abstraction that provides a convenient and effective mechanism for process synchronization. The second one is multiple processes may be active within the monitor at a time. Mutual exclusion is guaranteed by the operating system, and internal variables are only accessible by codes within the procedure. So, with monitors, yeah, it is a high level abstraction provided for convenience. Then, yeah, monitor ensures that only one process will be active within the monitor at a time. So, this statement is wrong. Multiple processes cannot be active. Only one process can be active within the monitor at a time, and mutual exclusion is guaranteed, and internal variables are accessible by codes within the procedure. So the answer here is 2. Like B, answer is B. Multiple processes may be active within the monitor at a time. That is the incorrect statement. The other next question is, in Peterson's algorithm, if the turn variable is not present, that is, the solution uses only the flag variable. The resulting solution will violate mutual exclusion, progress condition, bounded weight, and none of this. So, if the turn variable is not present, then mutual exclusion can still be handled, but it will the resulting solution will violate the bounded weight condition. So this variable actually ensures that if the other for P1 and P2, P2's turn is set, it will get the it will get its turn. So bounded weight is ensured by this turn variable. So the answer here is C. Now, the next question, which of the following is incorrect? A counting semaphore can take integer values ranging over an unrestricted domain. Binary semaphore range only between 0 and 1. Binary semaphore can be implemented as counting semaphore. None of the above. So, yeah, counting semaphore can take a range of values. That is true. Binary semaphore, the values will be 0 and 1. And using a counting semaphore, we can, of course, implement binary semaphore. We just keep restrict the numbers to 0 and 1. So, here, all the statements are correct. So, none of the above, none of the statements are incorrect. So, the answer here is D. Mm, yeah, so the next question, in bounded weighting, mutual exclusion using test and set instruction for a system with n processes, the maximum number of times other processes may enter into critical session after a process has desired to do so, it's n minus 1. So there is another solution here which uses an array to track which process is waiting. So like P1 to Pn. So we'll have an array and we'll check in that order, and so it will round in a circular manner. So until we it end the one process enter the critical section, so n minus 1 processes can enter. So yeah, so the answer here is C n minus 1. So that is in the bounded weighting mutual exclusion solution using test and set instruction for a system with n processes. So maximum number of times other processes may enter into critical section after a process has decided to do so n minus 1. So because we are checking it in a circular manner. Max it is with after that this process will get its chance. Answer here is C. Yeah. The next question a process we have to match the following. One is deadlock one, deadlock two, starvation, and three, priority invasion. So a process may never be removed from the semaphore queue in which it is suspended. So that scenario is that starvation. The two or more processes are waiting indefinitely for an event that that can be caused by only one of the waiting process. So that is that two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting process. So that is the scenario of deadlock that we just discussed minutes ago. Then the third one is scheduling problem and low priority process holds the lock needed by a higher priority process. That is called priority inversion. So the option here is P is mapping to 2, Q is mapping to 1, and R is mapping to 3. So P is mapping to 2, R is mapping to 3, and Q to 1. So option here is C. The answer is C. Yeah. A producer consumer problem with unbounded buffer size semaphore. We saw a producer consumer problem with a bounded buffer size, right? So if it is an unbounded buffer size, like there is no limit on the size, there is no restriction. We don't need to worry if this like producer can keep on producing. So that's a scenario. Whereas a consumer cannot consume from an empty buffer, right? So that is the scenario here. Producer, there will not be any restriction because there is no bound on the buffer size. Whereas consumer will have a restriction on the it's I mean it cannot read from empty buffer, right? Um, what are the for a producer with the what are the semaphores needed for it? So as we can see here in the producer side, there is no bound on the buffer. So producer does not have any restriction. So the semaphores used on the producer side was empty and mutex. Okay. So empty was to check whether there is an empty slot, and mutex was to get access to the buffer. So now this empty checker is not needed because there is no condition, there is no limit on the buffer. So we don't need the some empty semaphore. Whereas on the consumer side, we are checking the weight full and mutex. Full is like to check whether there is any content in the buffer or not, and mutex again to get access to the buffer. So these two still needs because consumer still needs to check if the buffer is have any content before reading it. So mutex full and Mutex and full are the semaphore used at the consumer that is still needed, whereas the empty semaphore which was used at the producer side is not needed. So the answer here is mutex and full. The answer is B here. Yeah, so the next question, in the bounded buffer producer consumer problem, suppose that in the consumer process, the wait statements of the response to semaphore full and mutex have been interchanged. The resulting algorithm still works fine, may create problem when the buffer is full, may create problem when the buffer is empty. Uh, None of the other options. So if we interchange the order in which the full and mutex is called up, so there will be at the consumer end, right? So there is no issue. There won't be any problem created when the buffer is full, but there will be a problem. There may be a problem created when the buffer is empty. That's what we are checking at the consumer side. So there is a possibility. So the answer here is C. Excuse me. Answer here is C. Hmm. Yeah. Yeah. So this is a code snippet. Yeah. In the following code, two processes are using semaphore S1 and S2, both initialized to 1. P1 is calling wait of S1 followed by wait of S2. P2 is calling wait of S2 followed by S1. And signal is also in the same order in which they have called the wait. So these processes violate mutual exclusion, have potential for deadlock, can never enter into their critical sections. D, none of the above. So here, as we can see, this is equivalent to the same example that we saw when there was an deadlock scenario, right? So when initially both of them are initialized to 1, so P1 will execute wait of S1, right? So it will get the S1 lock and S1 becomes 0. Same way, P2 will execute wait of S2 and P2 will get the S2 lock and S2 will become 0. Now when P1 tries to get the S2 lock, it is already with P2. P2 have not released it. And so it will be waiting here. And P2 will come and try to get the S1 lock. So S1 lock is all with P1 and it have not released it. So both of them are waiting for a lock. So P2 is waiting for the lock that is with P1 and P1 is waiting for the lock with P2. So both will keep waiting in that busy loop. Both of them will not proceed at all. Okay, so the there is a possibility of there is a potential for a deadlock. So it all depends on the scheduling. Okay, if P1 calls wait S1, wait S2 back to back, then this issue will not come. So S1, P1 will get the lock S1, P1 will get the lock S2. And then if there is a scheduling change happening and it goes to P2, P2 will try to get S2. So S2 is already with P1. So it will be waiting here itself. Then P1 will go to its critical section. It will release S1 and then it will release S2. When it releases S2, P2 will get S2. Then P2 will again get S1 because that's already released. will get into the critical section and do. So that is one scenario. But another scenario is when a P1 executed the S1, and then P2 got scheduled. P2 executed S2. And now after this, if P2 executes S1, again P2 is waiting. Now after that, if it gets scheduled to P1, wait S2. So there is a potential for a deadlock here. So the answer is yeah. Yeah. Yeah, the next question. Select the incorrect option. Mhm. Process, select the incorrect option. Okay. A process must execute wait mutex before entering the monitor and signal mutex after leaving the monitor. The signaling process can use next to suspend themselves. The integer variable next counter is provided to count the number of processes suspended on next and none of the above. So this is from the part of implementation of monitor, which I didn't discuss in today's session. You can, if then we may not be in a position to complete this in the 2 hour session. So I had to skip that part. So, yeah, so this is done in that portion, sir, I've discussed. So, yeah, mutex, wait of mutex and signal of mutex have to be, it must be executed before entering the monitor and after leaving the monitor. So, this option is correct. Then the signaling processes can use next to suspend themselves. Yes, that is true. And the next count gives the number of processes suspended for. So all these three statements are correct. So the answer here is none of the above. And the next question, in Peterson algorithm, if the flag variable is not present, that is the solution uses only turn variable, the resulting solution will violate progress condition actually. So if flag variable is not used, instead if we only use the turn variable, then it can so happen that the one process itself keep on getting and the other doesn't get a chance at all. So for because turn variable is actually set from the other process as well. So if the flag is not there, it will affect the progress condition of the mutual exclusion solution. The answer here is B. So with this, yeah, the questions are done. If any doubts, you can put it in the chat or unmute and ask. Otherwise, we can close today's session. If there are no more doubts, then we can close the session. I hope there are no more questions. We can close the session. Thank you for joining. See you again on next Tuesday. Thank you.